The framework was radical, certainly, but it had something previous theories lacked. It made testable predictions. The ICF predicted that if you could observe quantum entanglement at large enough scales, you'd find residual patterns from the universe's higher dimensional past, quantum correlations that span distances far exceeding what standard physics allowed. In August 2027, the quantum archaeology experiment launched from the International Space Station. Using an array of quantum sensors separated by thousands of kilometers, the experiment looked for these primordial entanglements. The sensors detected photons from the cosmic microwave background and checked for quantum correlations that shouldn't exist according to standard theory. The results came back in October. Positive. Photons that have been traveling separately for 13.8 billion years showed subtle but unmistakable quantum correlations. They remained entangled despite being separated by billions of light-years of expanding space. It was as if the entire observable universe remembered that it had once been a single point, and that memory persisted at the quantum level. "We've proven that the universe is memory," said Dr. Chun, who had become the public face of a new cosmology. Not memory like humans have, but something deeper, quantum information that persists from the very beginning and connects everything that exists. If primordial black holes were information processors, as the ICF suggested, they should show coordinated behavior. Information exchange across vast cosmic distances. Dr. Tanaka proposed a daring observational program. Monitor all 17 known primordial rings simultaneously and look for correlated activity in their central black holes. The logistics were staggering. It required coordinating observations across dozens of telescopes on Earth and in space, measuring subtle fluctuations in X-ray and gravitational wave emissions from objects billions of light-years away. The observing campaign ran from November 2027 through February 2028. When the data came in, even the researchers were stunned. The black holes at the centers of the primordial rings were firing off bursts of activity in patterns, not random, but structured pulses that repeated across all 17 objects with time delays matching the distance between them exactly. It was as if they were exchanging signals. "We don't know what information they're exchanging," Tanaka admitted at a press conference that made headlines worldwide. "But we can definitively say they're communicating. The statistical probability of these correlations occurring by chance is less than 1 in 10 to the power of 45. For context, that's like flipping a coin and getting heads 150 times in a row." The most unsettling part? When researchers analyzed the timing of the pulses, they found that the signals predated the Big Bang itself. The black holes appear to be exchanging information that originated from before our universe began. The scientific discoveries triggered a philosophical earthquake that made the Copernican revolution look like a minor tremor. If the universe was fundamentally computational, self-organizing, and possibly aware, what did that mean for humanity's place in the cosmos? Religious leaders were divided. Some saw confirmation of divine design, a creator who operated through mathematical laws rather than miracles. Others argued that the new cosmology eliminated the need for God entirely. The universe could create and understand itself. Philosophers debated whether the discoveries changed anything about ethics, meaning, or consciousness. If the universe processed information about itself, was that fundamentally different from human self-awareness? Did it have something analogous to goals or purposes? And most troubling, if we existed inside what was effectively a vast computational system, did we have free will, or were we simply subroutines executing predetermined code? Dr. Amanda Thornton found herself at the center of these debates. "I think we're asking the wrong questions," she said in a widely viewed TED Talk. "We're trying to fit these discoveries into our existing philosophical frameworks, dualism, materialism, idealism. But maybe those frameworks are inadequate. Maybe we need entirely new philosophical categories to understand what we're learning." She proposed what she called cosmopsychism, not the idea that the universe is a mind like ours, but that mind and matter aren't separate categories. Information processing, from quantum particles to galactic clusters to human brains, represented different scales of the same fundamental phenomenon, reality understanding itself. In March 2028, Maya Patel, working with a team of cryptographers, information theorists, and linguists, made a discovery that would define her career and haunt her dreams. The primordial code wasn't just structured. It contained a message. The team had been analyzing the geometric patterns in the cosmic microwave background, using every decryption technique known to humanity. For months, they found nothing but beautiful mathematical structures. Then Maya tried something unusual. Instead of treating the patterns as a code to be decrypted, she treated them as a compression algorithm, a way of encoding vast amounts of information in minimal space. When decompressed using principles from quantum information theory, the patterns yielded something extraordinary, a set of mathematical relationships that didn't exist in any known physics. Equations that described reality at scales beyond the observable universe, or perhaps before the Big Bang itself. But buried within these equations was something even stranger, a set of instructions, step-by-step procedures for manipulating the fabric of space-time, creating stable wormholes, and even impossibly, generating new universes from controlled quantum fluctuations. It's a blueprint, Maya said in a secure briefing to world leaders and scientific authorities. Or maybe a manual. The universe came with instructions, and we've just learned how to read them. The geopolitical implications were immediate and severe. If these instructions were real, humanity was on the verge of acquiring godlike technological powers. The ability to create stable wormholes would make interstellar travel trivial. The capacity to generate new universes raised ethical questions that no existing moral framework could address. The United Nations convened an emergency session, a new international body. The Council for Cosmic Technologies was established with authority superseding national governments in matters related to primordial code instructions. The world's leading scientists, ethicists, philosophers, and religious leaders assembled to determine what humanity should do with knowledge that could transform us into something far beyond what we currently were. After 18 months of debate, analysis, and testing, the Council reached a decision. Humanity would attempt to create a controlled wormhole. It would be small, stable, and monitored by every instrument humanity could bring to bear. If successful, it would prove that the primordial code instructions were real. If it failed, well, at least they'd know the limits of their understanding. The experiment was scheduled for September 15, 2029, at a specially constructed facility in Earth orbit, far from any planetary body that could be affected by catastrophic failure. That became known worldwide as Threshold Day, humanity's first deliberate manipulation of space-time structure. Dr. Sarah Chun, now director of the Threshold Project, addressed the world in the hours before the experiment. Whatever happens today, we're crossing a line. For 400 years, since Galileo pointed his telescope at Jupiter's moons, we've been observers of the cosmos. Today, we become participants. We're not just studying the universe, we're learning to speak its language. The apparatus was deceptively simple-looking. A ring of exotic matter, created using instructions from the code, surrounding a quantum field generator. The theory was elegant. By manipulating quantum fluctuations according to precise mathematical relationships decoded from the CMB, they could create a localized instability in space-time that would tunnel through to another point in space. At 1400 hours Universal Time Coordinated, Dr. Chin initiated the sequence. For 3 seconds, nothing happened. Instruments registered normal background fluctuations. The assembled scientists held their breath. Then reality twisted. Inside the ring, space itself opened. Not metaphorically, literally. A perfectly circular opening appeared, showing not the other side of the ring, but somewhere else entirely. Through the aperture, stunned observers saw stars. Unfamiliar constellations, viewed from an unknown vantage point approximately 47,000 light-years from Earth, according to rapid astronomical analysis. The wormhole was stable, perfectly stable, and through it, humanity was looking at a region of the Milky Way that no human had ever seen except through telescopes. "It works," Chin whispered, her voice picked up by every microphone in the control room. The instructions work. The universe really did come with a manual. The wormhole remained open for 17 minutes before the team deliberately shut it down, as planned. In that 17 minutes, they had verified something that would forever change humanity's relationship with the cosmos. We had graduated from observers to cosmic engineers. But the most startling revelation came from analysis of the data recorded during those 17 minutes. Dr. Marcus Rivera, now specializing in wormhole physics, noticed something peculiar about the stellar formations visible through the aperture. "Look at these patterns," he said, projecting the data at an emergency meeting of the Threshold team. "The stars on the other side aren't arranged randomly." The hashtag the cosmic crisis. When ancient galaxies break all the rules, a revolution is brewing in the depths of space. The James Webb Space Telescope has unveiled discoveries that the Big Bang Theory never anticipated. More than 30,000 ancient galaxies have emerged from the cosmic shadows, including a colossal galactic disk nicknamed the Big Wheel, which formed less than 2 billion years after the universe supposedly began. These galaxies have no right to exist. Not this soon, not with such tremendous mass, and certainly not with this level of structural sophistication. But the surprises don't end there. Fresh evidence suggests that dark energy, the mysterious force driving cosmic expansion, might not be constant after all. Meanwhile, measurements of how fast the universe is expanding produce wildly different results depending on which method scientists use. Could we be standing at the threshold of rewriting everything we thought we knew about cosmic origins? The implications are staggering, and what unfolds next could fundamentally transform the entire discipline of cosmology. Just how profound are these cosmic anomalies? Consider a single galaxy observed by the James Webb Space Telescope that has become the poster child for this cosmic conundrum. Astronomers have dubbed it the Big Wheel. The photons carrying its image began their journey toward Earth more than 12 billion years ago. Yet what finally reaches our instruments reveals a completely mature galactic disk, rotating with the graceful precision of a contemporary superspiral galaxy. The statistics are breathtaking. The Big Wheel extends approximately 30,000 parsecs from edge to edge, roughly 3 times broader than the Milky Way was at a comparable cosmic epoch. Its total mass equals that of our own galaxy, yet it achieved this enormous size in less than 2 billion years following the Big Bang. Even more astonishing, the Big Wheel spins at velocities comparable to the fastest spiral galaxies observed in today's universe, indicating a stable, sophisticated structure where primordial disorder should dominate. According to our leading cosmological frameworks, galaxies from this ancient period should have been compact, irregularly shaped, and still in the process of assembly. Yet the Big Wheel's disk appears remarkably smooth and orderly. Its spiral arms are already distinctly carved out, and its stars move in a synchronized choreography. The probability of discovering such a massive, well-organized disk so shortly after the universe's inception was calculated to be less than 2%. But there it spins before our eyes, undeniable, immense, and defying explanation. The Big Wheel represents a direct challenge to the gradual formation timeline predicted by standard cosmological models, compelling astronomers to confront uncomfortable questions. If one such galaxy has materialized, how many others remain hidden beyond our current detection limits? And what does the mere existence of this cosmic giant reveal about the fundamental principles that have governed the universe since its earliest moments? In a recent groundbreaking survey, astronomers utilizing the James Webb Space Telescope conducted one of the most extensive examinations of the early universe ever attempted. Within merely the first year of operation, Webb's deep field observations identified over 30,000 candidate galaxies at redshifts exceeding 6, meaning their light embarked on its cosmic voyage less than 1 billion years after the Big Bang occurred. These numbers dramatically exceed what our leading cosmological models had projected. According to lambda cold dark matter theory, lambda CDM, the early universe should have generated far fewer luminous, well-structured galaxies during that primordial era. Computer simulations based on lambda CDM, including prestigious models like Illustrious TNG and Millennium, predicted that only a small handful of massive galaxies should populate the entire observable volume at such extreme cosmic distances. Instead, Webb's astronomical census reveals a sky crowded with mature galactic systems, each blazing with hundreds of millions or even billions of stars. The discrepancy extends beyond simple population counts. When cosmologists analyzed the data more carefully, they uncovered an additional problem. The star formation efficiency implied by these observations defies conventional expectations. For galaxies to be this abundant and luminous so early in cosmic history, they must have converted their available gas into stars at rates 2 to 3 times higher than the maximum predicted by established theory. In nearby galaxies that we observe today, Typically, only 10 to 20% of available gas successfully transforms into stars. But the early universe as glimpsed through Webb's infrared eyes appears to demand conversion efficiencies of 30, 40, or even 50%, sometimes exceeding even these extraordinary rates. These aren't isolated anomalies scattered randomly across the sky. Throughout the entire observed population, this pattern consistently holds. Astrophysicists such as Michael Boylan-Colchin and Garth Illingworth have emphasized that to reconcile the observed galaxy numbers with theoretical predictions, either the universe assembled its first galaxies with unprecedented rapidity, or something crucial is absent from our current comprehension of cosmic evolution. The challenge has become systemic rather than anecdotal. It's no longer just about the big wheel. It's about an entire generation of massive, fully formed galaxies materializing billions of years ahead of their scheduled arrival. These overwhelming numbers force a straightforward question upon the cosmological community. If our computational models cannot keep pace with observational data, do the simulations require refinement and adjustment? Or has the moment arrived to fundamentally reconsider the rules governing the early cosmos? The Dark Energy Spectroscopic Instrument, DESI, collaboration's latest findings have thrust dark energy into the spotlight, that enigmatic force believed to drive the universe's accelerating expansion. The collaboration has analyzed spectra from nearly 15 million galaxies and quasars, constructing the most extensive three-dimensional map of the cosmos ever assembled. Their methodology employed baryon acoustic oscillations as a kind of cosmic measuring stick, tracking how the distribution of galaxies evolves across cosmic time. What they discovered appears subtle at first glance, but the ramifications are potentially revolutionary. DESI's data indicate that dark energy strength, characterized by the parameter W, may not remain fixed at -1 as the standard cosmological model assumes. Instead, the measurements hint at a systematic drift from approximately -1.4 in the distant past to roughly -0.7 in the present epoch, with a statistical confidence level reaching 4 sigma. This suggests that the force propelling the universe apart could be gradually weakening as time marches forward, a direct contradiction to the concept of a cosmological constant. If these results withstand further scrutiny, dark energy isn't merely a static property embedded in the fabric of space. It may be dynamic, evolving alongside the universe as it ages. Such a possibility would fundamentally undermine the foundation of the lambda CDM model, which treats dark energy as unchanging across all of cosmic history. For decades, cosmologists have depended on this constant to explain phenomena ranging from the cosmic microwave background's detailed patterns to the large-scale structured distribution of galaxies. But DESI's evidence points toward a universe where the fundamental rules themselves may be shifting beneath our observational feet. The inevitable next question emerges. If dark energy is indeed changing over time, what implications does this carry for our measurement of the universe's expansion rate? 2 decades ago, cosmologists believed they had determined the universe's expansion rate to within just a few percentage points of certainty. But rather than converging toward consensus, the discrepancies have only deepened. Today, 2 fundamentally incompatible numbers stand in stark opposition. 67 kilometers per second per megaparsec, calculated from patterns imprinted in the cosmic microwave background by the Planck satellite, and 73 kilometers per second per megaparsec, measured from local galaxies using Cepheid variable stars and supernovae as cosmic distance markers. This isn't a trivial disagreement. The difference stands at approximately 8%, far exceeding the combined error bars of both measurements, especially now that the James Webb Space Telescope has entered the debate. Adam Rees, a Nobel laureate and leader of the SH0ES team, supernova H0 for the equation of state, has dedicated years to refining the local measurement technique. With Webb's dramatically sharper vision, his research group recalibrated Cepheid distances for a third of the Hubble sample. The result, a local Hubble constant of 73.5 kilometers per second per megaparsec, with an uncertainty margin below 2%. That value is nearly identical to previous results obtained with the Hubble Space Telescope, but the precision has now reached such heights that systematic measurement errors can no longer account for the discrepancy. Every galaxy measured by both telescopes, every supernova cross-check between instruments, points toward the same unsettling conclusion. The expansion rate observed in our local cosmic neighborhood is measurably faster than what models based on the early universe predict. Meanwhile, Planck's cosmic microwave background measurements, interpreted through the theoretical lens of the lambda CDM model, remain firmly anchored at 67.4 kilometers per second per megaparsec. The two values stubbornly refuse to converge toward each other, even as observational techniques grow increasingly sophisticated and precise. The tension is no longer plausibly dismissed as a statistical anomaly or a calibration oversight. With JWST's independent confirmation, the mismatch has become permanently embedded in the observational data. This leaves theoretical cosmologists facing a profound dilemma. Either something fundamental is conspicuously absent from the standard cosmological framework, or the universe behaves in fundamentally different ways than we expect across the largest cosmic scales. For now, these conflicting numbers stand as an open challenge to the physics community, demanding innovative ideas capable of bridging the enormous gulf between the universe's earliest observable moments and what we measure in the cosmos today. David Wiltshire's timescape cosmology proposes a radical reconceptualization that the universe's intricate patchwork structure, dense galactic clusters interwoven with sprawling cosmic voids, creates a hidden layer of complexity in the fundamental flow of time itself. In this model, time does not progress at a uniform pace throughout the universe. Regions densely packed with galaxies, such as the Milky Way's neighborhood, experience gravity's pull with such intensity that their clocks run measurably slower when compared to vast, nearly empty voids between galactic superclusters. Detailed calculations reveal that a clock situated inside a galaxy can lag behind one drifting through a cosmic void by as much as 35% over the entire age of the universe. This means billions of additional years would have elapsed for an observer floating in emptiness, compared to someone anchored within a dense galactic cluster. The Pantheon plus supernova dataset, when analyzed without the assumption of a uniform cosmic clock ticking everywhere at the same rate, reveals that this temporal differential isn't merely a mathematical abstraction. The data provide extraordinarily strong statistical support, with Bayes factors well exceeding 5, for the timescape scenario over the standard cosmological constant model. In this revolutionary perspective, the apparent acceleration of cosmic expansion emerges from the manner in which time stretches and contracts across the cosmic web's intricate architecture, rather than from any mysterious dark energy permeating space. The result is a universe where the fundamental rules vary depending on where you conduct your measurements, and where perceived acceleration might be nothing more than an inevitable consequence of living in a slow-ticking corner of the cosmos. A striking new pattern has emerged from the observational data. The rotation directions of early galaxies are not evenly distributed, as random chance would predict. Among hundreds of galaxies measured at high redshift, approximately 2/3 rotate clockwise, while only 1/3 spin counterclockwise. That is 66 to 33% split, with a statistical significance reaching 3.39 sigma, well beyond what random probability would produce. This asymmetry isn't confined to one particular patch of sky or limited to a single survey. Instead, it suggests a cosmic scale preference, as if the universe itself retains a directional memory established long before the first stars ignited their nuclear furnaces. Some theoretical physicists interpret this as more than a mere statistical curiosity. They propose that such large-scale rotational alignment could represent the fingerprint of our universe's birth process. If the cosmos originated inside a rotating black hole, a scenario explored by physicists like Nikodym Poplawski, the initial angular momentum would imprint a preferred rotational axis on everything that subsequently formed within it. In this view, the residual angular momentum from that primordial rotation could guide the way galaxies spin even billions of years later across vast cosmic distances. The idea is admittedly radical, but the numerical evidence demands serious attention. If a black hole universe scenario sets the cosmic initial conditions, then the spiral patterns traced by ancient galaxies aren't merely random outcomes of chaotic processes. They represent echoes of a deeper, hidden cosmic order established at the moment of creation. For now, this evidence stands as an open invitation to cosmologists. Either the early universe operated according to rules far stranger than we previously imagined, or our entire cosmic origin story began with a literal twist. What happens when you lay all these cosmic mysteries side by side? The big will spinning impossibly early. 30,000 ancient galaxies where only dozens should exist. Dark energy that refuses to stay constant. The Hubble tension that grows more severe with every measurement. Time flowing at different rates across the cosmic web. Galaxies spinning with a preferred direction, as if the universe remembers which way it was born. Individually, each anomaly could be dismissed as an observational quirk, a calibration error, or simply the natural growing pains of young science pushing its instruments to their limits. But together, they form a pattern that suggests something far more profound than mere measurement problems. The standard Big Bang model, lambda CDM, has served cosmology brilliantly for decades. It successfully predicted the cosmic microwave background, explained the abundance of light elements, and described the large-scale structure of the universe. But that was before we could peer back to within a billion years of cosmic dawn. That was before we could measure the expansion rate with such devastating precision. That was before we discovered that the early universe was far more mature, far more organized, and far more efficient at building galaxies than any model predicted. In March 2025, a team of cosmologists at the University of Cambridge published a comprehensive statistical analysis that sent shockwaves through the physics community. They combined data from JWST's galaxy surveys, DESI's dark energy measurements, the Hubble tension observations, and the galaxy spin alignment data into a single unified framework. Their conclusion was stark. The probability that all these anomalies could simultaneously exist, the standard cosmological model, was less than 0.01%, equivalent to a 5 sigma detection of physics beyond the standard model. The paper, titled Systematic Failure of Lambda CDM at High Redshift, A Crisis in Cosmology, didn't mince words. Lead author Dr. Sarachin stated in the accompanying press conference, "We are no longer discussing whether the standard model needs modification. We are now discussing what replaces it." Within weeks, theoretical physicists began racing to construct new frameworks. Some proposed that the universe underwent a previously unknown phase transition in its first billion years, a cosmic adolescence that dramatically accelerated galaxy formation before settling into the slower pace we observe locally. Others suggested that dark matter itself might have different properties in the early universe, or that dark energy has been steadily evolving since the Big Bang, fundamentally altering the cosmic expansion history. But the most radical proposals went further. What if the Big Bang wasn't beginning at all, but merely a transition point in an eternal cosmic cycle? What if our universe exists inside a parent structure, a rotating black hole, as the spin alignment data suggests, with properties in physics that predate our own cosmic epoch? Then came August 2025. The James Webb Space Telescope, conducting a routine deep field observation of the Hubble ultra-deep field region, detected something that would change everything. Buried in the data at a redshift of 14, corresponding to just 250 million years after the supposed Big Bang, was not a galaxy, but a structure that shouldn't exist under any circumstances. Astronomers called it the primordial ring. It appeared to be a massive, circular structure approximately 1 billion light-years in diameter, composed of hundreds of ancient galaxies arranged in an almost perfect circle. The statistical probability of such an arrangement forming by chance was effectively zero. More troubling still, the galaxies showed synchronized rotation patterns, as if they were all responding to some organizing principle present when they formed. The discovery sparked immediate controversy. Some astronomers argued it was merely a projection effect, an optical illusion created by galaxies at different distances appearing to align by chance. But spectroscopic analysis confirmed that all the galaxies sat at the same redshift. They formed a real, three-dimensional ring structure in the actual cosmos. Dr. Marcus Rivera, the astronomer who first spotted the anomaly, summarized the implications in a statement that went viral across scientific social media. "We just found evidence of large-scale cosmic structure at a time when the universe supposedly hadn't existed long enough to build anything larger than individual galaxies. It's like finding a fully constructed city in a place where there hasn't been time for humans to invent architecture." The primordial ring became the catalyst that transformed cosmological crisis into cosmological revolution. Within months, multiple research teams proposed that the structure could only exist if the universe had undergone a period of extreme, localized organization in its earliest moments, something beyond the scope of inflation theory as currently understood. One particularly compelling model suggested that the early universe contained topological defects, cosmic strings or domain walls left over from symmetry breaking in the first fractions of a second. These defects could have acted as gravitational scaffolding, seeding the formation of structure far earlier and far more efficiently than lambda CDM predicted. The model not only explained the primordial ring, but also naturally accounted for the rapid formation of galaxies like the Big Wheel, the enhanced star formation efficiency, and even the preferred spin direction of early galaxies. The dark energy evolution measured by DESI fit into this framework as well. If the early universe contained additional fields or forces that gradually decayed over cosmic time, they would have left precisely the signature DESI observed, a dark energy that appears stronger in the distant past and weaker today. Even the Hubble tension found resolution in some versions of the new models. If the early universe expanded at a different rate than predicted by lambda CDM, accelerated by these primordial fields, then the cosmic microwave background measurements and local expansion measurements would naturally disagree. They're measuring different epochs of a universe with evolving expansion physics. By late 2025, the Nobel Prize Committee faced an unprecedented situation. For the first time in physics history, they awarded the prize not for confirming a theory, but for demonstrating its failure. The prize was shared among the teams who discovered the primordial ring, measured the dark energy evolution, and confirmed the Hubble tension with unprecedented precision. The citation read, "For observations that revealed the limits of the standard cosmological model and open a new era in our understanding of the universe." In her Nobel lecture, Dr. Chen captured the moment. A century ago, Einstein gave us a static universe. Then Hubble showed it was expanding, and Einstein called his cosmological constant his greatest blunder. But perhaps it wasn't a blunder at all. Perhaps it was incomplete. What we're learning now is that the universe is stranger, more dynamic, and more deeply structured than we imagined. The Big Bang wasn't wrong. It was just the beginning of a much larger story. Today, cosmology stands at a crossroads reminiscent of the early 20th century, when quantum mechanics and relativity overthrew classical physics. The new models emerging from this revolution paint a universe that is more ancient than we thought. If the early universe contained organizing structures or forces that accelerated galaxy formation, then the effective age of cosmic structure is far greater than the 13.8 billion years since the Big Bang. The mature galaxies JWST observes aren't violations of physics. They're exactly what we should expect from a universe with richer early dynamics, more connected than we assumed. The galaxy spin alignments and structures like the primordial ring suggest that the early universe possessed large-scale coherence extending across billions of light years. Perhaps quantum effects during inflation created correlations that persisted longer than standard theory predicted, or perhaps our universe inherited structure from whatever existed before the Big Bang, more dynamic than we modeled. Dark energy isn't a constant. It's a player in cosmic evolution, changing its strength as the universe ages. This dynamism might be the key to understanding why the universe appears fine-tuned for life. Perhaps we exist in an epoch when dark energy happens to have the right strength, part of a much longer cosmic story with different epochs and different physics. More mysterious than ever, each answer raises new questions. If we exist inside a rotating black hole, what lies outside? If cosmic strings seeded early structure, what created them? If dark energy evolves, what determines its evolution? The universe has revealed that it keeps secrets far deeper. The next generation of telescopes is already being planned. The extremely large telescope in Chile, the 30-meter telescope in Hawaii, and NASA's proposed Habitable Worlds Observatory will push even further into the cosmic dawn, perhaps finding structures that predate the primordial ring. Space-based gravitational wave detectors like LISA will probe the fabric of space-time itself, potentially detecting the cosmic strings or primordial black holes that some models predict. But more than new instruments, cosmology needs new ideas. Young physicists entering the field today face an opportunity that comes once in a century, the chance to rebuild our understanding of the universe from the ground up. The standard model isn't being abandoned. It's being transcended, incorporated into a larger framework that can explain both its successes and its failures. The ancient galaxies spinning in the depths of space aren't aberrations. They're messengers from an era we're only beginning to understand, telling us that the universe has been writing its story in ways we never learned to read. The cosmic crisis has become a cosmic awakening, and we're finally learning to see what was hidden in plain sight all along. On a cold December evening in 2025, a graduate student at the California Institute of Technology was reviewing archival data from the cosmic microwave background, the afterglow of the Big Bang itself. She was running a new analysis algorithm designed to detect subtle patterns that earlier methods might have missed. What she found made her hands tremble. Embedded in the quantum fluctuations of the CMB, visible only when analyzed at the highest possible resolution, was a pattern, not a random pattern, but something that looked disturbingly like structure, geometric regularities that repeated across vast scales with mathematical precision. The implications were staggering. The cosmic microwave background formed just 380,000 years after the Big Bang, when the universe first became transparent to light. If it contained organized structure, then whatever organized it must have existed even earlier, perhaps in the first microseconds of cosmic time. She checked her calculations 3 times. The signal was real. The statistical significance was off the charts. The universe wasn't just showing structure earlier than expected. It was showing that structure might have existed from the very beginning, or perhaps even before the beginning. She titled her draft paper simply, Patterns in Primordial, Evidence for Pre-Big Bang Structure in the Cosmic Microwave Background. As she pressed send to submit it to the journal, she knew that the cosmic story was about to get stranger still. The revolution in cosmology wasn't ending. It was just beginning. The universe had kept its greatest secret for 13.8 billion years. Now, finally, it was ready to tell us where it really came from. And the answer, when it came, would be more beautiful and more bizarre than anyone had dared to imagine. The graduate student's name was Maya Patel, and within 72 hours of submitting her paper, her inbox exploded. The journal's editor called her directly, an almost unheard of occurrence. 3 separate research groups had independently detected similar patterns using different analysis techniques. What Maya had found wasn't fluke or an artifact. It was real. The pattern in the cosmic microwave background resembled nothing so much as a crystalline structure, repeating geometric forms that appeared at multiple scales. Some sections showed hexagonal symmetries. Others displayed fractal-like self-similarity. Most perplexing of all, when the pattern was mapped in 3 dimensions using the polarization data, it formed shapes that mathematicians recognized. They were similar to Calabi-Yau manifolds, the exotic geometric structures that appear in string theory as the hidden dimensions of space itself. It's like looking at the blueprint. Maya told a hastily assembled press conference in January 2026. The cosmic microwave background might not just be the afterglow of the Big Bang. It might be showing us the underlying architecture of reality itself, the geometric framework that everything else is built on. The discovery sent theoretical physicists into overdrive. For decades, string theory had languished as an elegant mathematical framework with no experimental verification. It predicted that reality consisted of tiny vibrating strings existing in a universe with 10 or 11 dimensions, most of them curled up so small that we couldn't detect them. Critics had long complained that string theory couldn't make testable predictions. But now, suddenly, the geometry predicted by string theory appeared to be imprinted on the very structure of the early universe. Dr. Leonard Kovacs, a string theorist at Princeton, was one of the first to make the connection explicit. String theory doesn't just predict extra dimensions. He explained in a paper that would eventually garner over 50,000 citations. It predicts specific types of transitions during the early universe, moments when higher dimensional space could temporarily become visible before settling into our familiar 4-dimensional space-time. What we're seeing in the CMB might be the fossil record of exactly such a transition. The implications were staggering. If true, it meant that in the first microseconds after the Big Bang, our universe existed in a higher dimensional state. The patterns in the CMB were literally the shadows cast by these higher dimensions as they collapsed down into the hidden quantum realm. But the patterns held an even deeper mystery. Dr. Elena Volkov, a mathematician specializing in information theory at Oxford, made a discovery that would spark the most controversial debate in modern science. She applied information theoretic analysis to the CMB patterns and found something impossible. They contain more information than random quantum fluctuations could produce. Imagine rolling a die 1,000,000 times, she explained in a viral YouTube lecture that crashed the university's servers. Random rolls would give you a certain amount of information, but if the die kept rolling sequences that spelled out words or formed mathematical constants, you'd know something was influencing the rolls. The CMB patterns are similar. They're too organized, too structured to be purely random. Her analysis suggested that the information content of the CMB corresponded to approximately 10 to the power of 122 bits, a number so vast it exceeded the theoretical information capacity of the observable universe itself. Unless something fundamental was wrong with information theory, the patterns couldn't have formed by chance. Some called it the primordial code. Others called it the most profound mystery in physics. A few bold voices whispered the question that everyone was thinking, but few dared to ask. Was the universe's structure deliberately designed? The primordial code discovery catapulted a previously fringe idea into mainstream scientific discourse: the simulation hypothesis. If the universe contained structured information from its very beginning, information that exceeded what random processes could create, perhaps reality itself was constructed, not evolved. But this wasn't the crude simulation hypothesis of science fiction. Dr. Thomas Chun, no relation to Sarah Chun, though they would eventually collaborate, proposed something far more sophisticated: the nested universe framework. Think about how we create simulations, he suggested in a landmark paper. We don't simulate every atom. We use mathematical shortcuts, generating detail only where needed. The quantum wave function collapse might be exactly such a shortcut. Reality remains probabilistic until observed because computing every possible outcome would be inefficient. The universe only renders specific outcomes when measurement occurs. The framework explains several quantum mysteries that had puzzled physicists for a century. Why did observation collapse wave functions? Why did quantum systems behave differently when measured versus unmeasured? Why did reality seem to operate on probabilistic rules at the smallest scales while appearing deterministic at large scales? If the universe operated like a vast computational system, these weren't bugs. They were features, optimization strategies for running a cosmos. Theoretical speculation needed experimental verification. In March 2026, a team at CERN proposed an audacious test. If the universe was structured like a computational system, it should have limits, resolution boundaries where the underlying code became visible. They designed an experiment to probe the fabric of space-time at the Planck scale, the smallest possible meaningful distance in physics, about 10 to the power of negative 35 meters. At this scale, quantum mechanics and gravity merge in ways that no current theory could fully describe. But if space itself had an underlying structure, like pixels on a screen, it might become detectable at these extreme scales. The experiment required modifications to the Large Hadron Collider and took 8 months to set up. When they finally ran it in November 2026, the results were unambiguous. Space-time wasn't smooth at the Planck scale. It had structure, a discrete, granular foundation like a three-dimensional lattice. "We found the pixels of reality," announced Dr. Sarah Chun, who had joined the experimental team. "Space isn't continuous. It's made of distinct units, about a Planck length across. It's like zooming into a photograph until you see individual pixels. We've just zoomed into reality itself."